Please join me in welcoming Professor Scott Tremaine, Chair of the Selection Committee for the Shaw Prize in Astronomy and Professor at the University of Toronto, Canada, and the Institute for Advanced Study in Princeton, USA. Hello, Professor Tremaine.
Hello, Leon.
Can you please tell us more about astrometry? What does it study, and what is the history behind it?
The history of astrometry goes all the way back to the dawn of humanity. For tens of thousands of years, humans have watched the stars and planets and how they move. The quantitative study of these motions is the oldest scientific discipline, and written catalogs of stars and their positions date back all the way to the Babylonians. Since the invention of the telescope, star catalogs have grown dramatically in size and accuracy. However, by the late 20th century, the measurement of stellar positions, often called astrometry, from ground-based optical telescopes encountered insurmountable barriers to further improvements, arising from the atmospheric distortions that make stars twinkle, small distortions of the telescopes themselves due to their own weight and to time-varying thermal stresses, and the difficulty of stitching together data from telescopes in different continents that see different parts of the sky.
I can already imagine how challenging it was. So how were these obstacles overcome?
Soon after the launch of the space age in the 1950s, astronomers recognized that a space-based telescope could do astrometry far more accurately than any ground-based telescope. But it took more than 2 decades before the first astrometric telescope, called Hipparchus, was launched by the European Space Agency in 1989. The successor to Hipparchus, called Gaia, was launched in 2013 and is planned to operate at least until 2025. Both Gaia and Hipparchus are based on the same design principle, a pair of telescopes pointing approximately at right angles, whose fields of view are combined on a single image. In contrast to an imaging telescope like the Hubble Space Telescope, which points in a fixed direction and takes long exposures, the Hipparchus and Gaia's telescopes spin slowly across the sky and measure the positions of stars by the times when they cross a fixed grid on the image field. Despite this similarity in design, Gaia is far more powerful than Hipparchus, producing a catalog that's 10,000 times larger and 100 times more accurate. The capabilities of Gaia are astounding even to professional astronomers. The Gaia catalog contains almost 2 billion sources, stars, galaxies, and quasars. Gaia can measure changes in the positions of stars as small as the size of a teacup held by an astronaut on the moon, and motions as small as the rate of growth of the astronaut's hair.
Wow, well, the level of accuracy is astonishing. And how important are these measurements to the study of the cosmos at large?
The measurements produced by Hipparchus and Gaia provide fundamental data that underpin almost every aspect of modern astronomy and astrophysics. Astrometric distances are used to calibrate all distances in astronomy and form the foundation for measuring the size of the universe. Accurate distances to stars allow us to measure their intrinsic luminosity, and this in turn is a sensitive probe of their internal physical processes. Measurements of the velocities of stars allow us to infer their galactic orbits, which in turn provide insight into the formation and history of the Milky Way and the distribution of the mysterious dark matter within it. Gaia will also provide a rich harvest of ancillary astronomical results, including an all-sky survey of the brightnesses and colors of 1 billion stars, light curves of hundreds of thousands of variable stars, thousands of newly discovered extrasolar planets, a survey of asteroids and other small solar system bodies with unprecedented detail, the discovery of hundreds of thousands of distant quasars, and stringent new tests of Einstein's theory of gravity. Hipparchus and Gaia succeeded because of the sustained collective effort of hundreds of researchers, managers, and engineers over the past half-century. The 2022 Shaw Prize in Astronomy is awarded in equal parts to 2 of these individuals, Leonard Lindegren and Michael Perriman, for their lifetime contributions to space astronomy and for their role in the conception and design of these 2 missions. The award is also intended to honor the much larger community that made Hipparchus and Gaia possible.
Thank you, Professor Tremaine.